Today we're talking about the length around the circle, but we're not going all the way around. If we went all the way around, that's the circumference, and we've already talked about that. We want to know, what about just part of the way around? How far is it from here to here, for example, or from here to here? So it's part of the circumference, but it's not the entire circumference. It's going to be a fraction of the circumference. So we're going to start off with a small little introduction here, and I'm not going to use all three circles. I'll just use one of them to kind of introduce this concept. Remember, we have taken a look at the relationship between a central angle and the measure of its arc. Let's diagram that first so we know what we're talking about here. As you know, it's 360 degrees all the way around the circle, and this happens to be divided into 8 different arcs. So if we took 360 and we divide that into 8, you know that each of these would have an arc measure of 45 degrees. I'll just fill that in here. And that should add up to 360 degrees total. We've learned that the angle is going to be, the central angle is going to be the same as the arc measure. So if this is a 45 degree arc, this is a 45 degree central angle. And these also add up to 360 degrees. In this particular circle, we're using a circle where the diameter is 6 centimeters. In fact, you can see that right here. We've drawn it to scale. So if you hold up the ruler to that, you can see, in fact, yes, we do have a diameter of 6 centimeters. So that means our radius should be half the size. And sure enough, 1, 2, 3 centimeters it is. So I'll just jot that down right here. This is a circle with radius of 3 centimeters. So what we're asking today is, how many centimeters along the edge of the circle is it from here to here? We know the circumference would be in centimeters as well. We could calculate that using pi times diameter, but we're not using the entire circumference. We're using only a portion of the circumference. So how would you do that? It's really hard to put your ruler up to the circle and turn it accurately and expect to have any sort of real value. It looks like it's about 1 centimeter, and maybe it's 2 centimeters. I don't even know. So we want a method where we can calculate it exactly. So let's gather some data in this chart below. Again, this was originally set up for exploring all three circles. We'll just use the big circle. So we do know that the central angle is 45 degrees, so we figured that one out. I'll just jot that here in the middle line. What we're going to do is we're going to set up a ratio. So take a look at this ratio. We're saying, let's take that central angle, put it on the top, and let's put the total angle around the circle. That's your 360 degrees. So if you put 45 degrees on the top and 360 degrees on the bottom, well, that reduces to 1/8, which makes sense because 45 degrees is 1 out of all the 8 parts that you see. If we were to look at the decimal value, that would be 0.125. So now let's take a look at the length. So that means in centimeters, and in centimeters, how far around the circle is it? So this is our circumference, which we know is pi times diameter. So pi times diameter, here again the diameter is 6. So 6 pi, there it is. But let's put that as a decimal, so that'll be 18.85, and that's in centimeters. And this arc length is describing the length around the circle of the arc. We know the arc measure is 45 degrees, but we're asking what is the length of that arc in centimeters, and that's what we're trying to figure out how to calculate. So in terms of looking for the patterns in the numbers on this particular page, we don't have that formula yet. We're just going to very casually measure it with a piece of string. And so if I were to take a piece of string and try to wrap it around the circle and say that's as far along the arc length as we get, and then hold that up to our ruler, it's about 2.5 centimeters, right? So again, it's not real precise, but that's what we'll go with right now, 2.5 centimeters. So we're now going to compare the ratio of the length to the length. We want the part of the length to the whole length. We want the arc length, which was the 2.5 centimeters, over the entire length around the circle. That was the circumference. That's 18.85. And we want to compare that result with the result we got previously. So if I type that in my calculator, I'm going to get something like 0.13. And so this is what we're trying to figure out. Where did I see that number before? Well, it's right here. If we round that to 2 decimal places, you can see it's really close. That's going to be my 0.13 and 0.13. So it's a little bit inaccurate to measure with a string, so we're a little bit off, but that's close enough. What we're saying is that these ratios are equal. These decimal values are equals, and they came from the ratios, and the ratios were set up like this. So if the decimal values are the same, then what we're now declaring is that this ratio equals this ratio. We have a proportion, in other words. The way in which we can calculate the distance around the circle, what we're calling this arc length, is if we put it in a proportion. So we're going to have this on one side of the equation, there's my equal sign, and we'll have this proportion on the other side of, we'll have this ratio on the other side of the equal sign, and with a proportion we can then cross multiply. So this is how we are going to be calculating arc length. So let's clean this up a little bit by turning to the next page. You'll see the formula presented to you. Right there in that box, it says, in a circle, the ratio, remember a ratio is a comparison of 2 numbers, the ratio of the length, so we're talking like centimeters or inches, the ratio of the length of a given arc to the length of the circumference. So that's what you're looking at right here. There's the arc length to the circumference, is equal to another ratio. What ratio did we use? We used the ratio of the measure of the arc, or the central angle, because it's the same thing, out of 360 degrees. So what we're representing is, in this fraction, we're representing the distance around the circle. So this is the part of the distance over the total distance. Our name for that is the circumference. And over here we have the ratio in degrees. This is the arc measure, which is the same as the central angle. So that's the part angle measure. And on the bottom is the total angle measure. And as you know, the total angle measure is 360. So the 360 always stays the same. That means we have 1, 2, 3 other fields that we have to put information in. And one of these will be the variable. Maybe the arc length is the variable. And we'll have a number in all the other places. We can cross multiply and solve for the arc length. Maybe the arc measure is the variable, in which case we can cross multiply. Or maybe the circumference is the variable, and again we can cross multiply. So let's look at a bunch of different examples to help us illustrate that concept. Here in example number 1, we're asked to find the arc length. All right, so the units happen to be in meters. So we're saying how many meters is it around the circle from point A to point B? We're using that. You can see the central angle is 88 degrees. So we know the number of degrees around the arc is 88 degrees, but we want to know how many meters is that. All right, step number 1, calculate your circumference. So circumference is, they have a radius here, so let's use 2 pi r. So I have its exact value at 4 pi. I have the decimal value of 12.57. That's the first thing we need. And the reason why I have to calculate that first is because in our formula, we need to put the circumference into this proportion. All right, step 2, now we build the proportion. And it says we want the arc length on the top, the circumference on the bottom. Well, now we have the circumference, which is the 12.57. Set that equal to another ratio. It says the arc measure. Now we're measuring it in degrees, right? So that's 88 degrees out of a total 360 degrees. So remember that when you have a ratio like this, the units cancel out, so degrees cancel out with degrees. So that's why the answer Won't be in degrees because the degrees are gone. And this is our variable right here, the arc length. So I am going to get it by itself. We're currently dividing by the 12.57, so I'm going to multiply both sides by 12.57. 12.57 cancels out on the left-hand side. This is my variable. It is now by itself. And this is what I type into the calculator. So go 88 times the 12.57, take that answer and divide by the 360, and that gives us our answer. Now we want to make sure we put the units on it. It's a length. The length is measured in meters, so our answer is in meters. All right, we're going to look at a few other variations on this in these next few diagrams. Let's take a look at part B. Here's our circle, center at Q. Notice that you have a radius right here. It's a decimal value of 12.3 feet. And this is around the arc from R to S. But it's not in degrees, it's in feet, which means this is a length. That 38 feet that you see right there, that is the arc length. In other words, we're starting with the arc length and kind of working backwards to find something else. They want us to find the measure of the arc. Remember the little m? That means you are looking for an answer in degrees. So we want how many degrees is it around the circle from R to S. So step number 1, find your circumference. All right, 2 pi r, so 2 times pi times the 12.3. And that'll give me a circumference of 77.28. Again, that's in feet. Right. Step number 2, now we're going to set up our proportion. So on the left-hand side, I'm using the arc length over the total circumference, and the arc length is given to us as 38 feet over the total circumference of 77.28. And because that's a distance, that's also in feet. And then on the right side, we want the number of degrees out of 360. Well, we don't have the number of degrees. No, that's because that's what we're asked to find. So this is my variable. It's the measure of the arc, RS. That's my variable. It's currently being divided by 360, so we're going to do the opposite. We will multiply both sides by 360. So there's my variable by itself on the right-hand side. On the left-hand side, you can see we have feet over feet, so the feet cancel out. That's why the units are not feet anymore, but degrees, because the degrees come from the 360 degrees. And we'll use the calculator. We'll go 360 times the 38, take that answer, and divide it by the 77.28. So we get 177.02, and again, that's in degrees. Notice it's not quite a semicircle, right? So this answer makes sense. If we had a semicircle, that'd be 180 degrees, and this is slightly less than 180 degrees, so it is roughly drawn to scale. Here is part C. They're asking us to find the arc length. That's the distance around the circle from point A to point B. Our units are in feet, so we want to know how many feet are there from point A to point B. We have a central angle of 97 degrees, which means this arc measures also 97 degrees. And the radius is 4 feet, like we said. So step 1, find your circumference. Circumference equals 2 pi r. That's a decimal value of 25.13. Again, that's in feet. Step number 2, we're going to build our proportion. So we want the arc length. That's what we have to find. So the arc length over the circumference, which we just figured out. That's the 25.13. That's in feet. Equals, now we want the degrees. We know it's always over 360 degrees. Do we have an angle measure? We do. That central angle of 97 degrees is the same as its arc measure, so we have 97 degrees around the circle from point A to point B. Notice the degrees cancel out. That's why our answer will not be in degrees. There's our variable. It's being divided by the 25.13, so we're going to multiply both sides. So we'll type into our calculator the 97 times the 25.313. We'll divide that by the 360, and this is our answer, 6.77, and that is in feet because that's the only units remaining in our proportion. So these three are fairly straightforward. This is the exception. This is where it gets a little bit weird. So we're going to talk about that here in a moment. I don't know if it's weird. I don't know if that's fair to say, but it'll feel different, I believe. All right, so we have set up our proportion, and in each case, we've always started with the first step of finding the circumference, and then the second step is using that circumference in the proportion itself. So now in this last part, we're taking a look at trying to figure out the circumference. Like, that was always our first step. We always started by finding the circumference because they gave us the radius that we could find the circumference. Here, I don't even have the radius. So how am I supposed to find the circumference if I don't have the radius? Well, remember, that could be your variable. And so in our proportion, that means the circumference will be our variable, and that will be here on this bottom of the fraction. So let's put capital C as the variable in place of that circumference. So here's our proportion. So in other words, we're skipping step 1 because we don't have a radius to calculate the circumference. We're going right to step 2, and that's setting up the proportion. So we need the arc length over the circumference. There's your arc length because it's in centimeters, 3.44 centimeters over your circumference. So I'm just using capital C for the circumference, and that will equal a number of degrees out of 360 degrees. And we have a 60-degree angle, which means the arc is 60 degrees around the circle from x to y. All right, so notice you have the degrees over degrees, so the degrees will cancel out, and the only units remaining are centimeters. So that's why our final answer will be in centimeters. Our variable is in the bottom, the denominator, so we need to cross multiply like this. So 60 times the circumference, 60 times c, equals 3.44 times the 360. And then we have to divide both sides by 60 to get the variable by itself. So that's how we calculate the circumference. Turns out we don't even need the radius. We're just using the proportion. We go to our calculator, we type in the 3.44 times the 360, all of that divided by 60, and I have 20.64. And again, the units are centimeters because the degrees canceled out, so it can't be degrees. And circumference is a distance around the circle, so we use centimeters to measure distance. All right, so those are some fairly traditional problems. We're going to take a look at a few others that are kind of mixing it up a bit. So we do have a few more examples to take a look on the next page. We're mixing it up, I say, and what I mean by that is we have a variety of questions here. There's 6 in this particular problem, and they're not all going to use proportions, only some of them. And so the trick here is to recognize when you need to use a proportion and when another method will work. All right, so here's some of our given information. We have a circle. The center is D. Notice we have 2 angles that are congruent. So let's mark that on our picture. Angle ADC. ADC is this one here in the top left. And BDC, that's this one here down here in the bottom. So I don't know what their measure is just yet, but they're the same size. So I'll just put an arc right there at the central angle just to indicate that they are going to be the same size. So let's find the measure of arc ACB. So we're starting at A, we're going around the circle past C, and we're ending at B. And you might say, that's an arc measure. Shouldn't we use the proportion? No, we should not, because they do give us a central angle of 101 on the right side, which means that this many degrees around the circle from A to B is 101 degrees. And the arc that we're trying to find is just everything else of the circle except not the 101. So we can simply subtract from 360. 360 minus the 101 means that we have 259. So it's 259 degrees around that circle, the major arc from A to B. So now let's find the minor arc from B to C. And if we find this one, it's the same as that one. So there's 2 of them that are the same size. So we're taking that information and just dividing it by 2. So each of these minor arcs is 129.5. So this one is 129.5, as is this one at the top. Remember, they all add up to 360 degrees. So notice we didn't even have to use a proportion here because we could find the numbers we needed from the given information at the central angle on the right-hand side and its arc. Now in part C, they're asking for the length. That's the new topic. That's what we've been studying today. That's where you have to have the proportion. So step number 1, find the circumference. Circumference is 2 pi r, and we have a radius here of 24.9 meters. That's the radius. So 2 times pi times the 24.9 gives us a result of 156.45. Step number 2, we set up the proportion. I want the arc length over the circumference, right? So there's the circumference, 156.45, equals something out of 360 degrees. So what angle measure should I use, or what arc measure should I use? We're looking for arc ACB. So we're starting at A, going the long way around the circle to C, and finishing at B. That's what we found here in part A. That arc measure is 259. So again, the degrees will cancel out, which means our answer will be in meters. I'll put that right there. And we need to solve for the variable. Let's multiply both sides by the 156. And there's our answer, 112.56, and that's in meters. Let's find another length. This time it's the length of CB, which is here. Now we have a couple of options. This is a length. That's a new topic. We could do this procedure all over again. Find the circumference, set up the proportion. But we know that this arc CB is half of the big major arc on the left-hand side, right? We took 259 degrees, which was the big arc on the left-hand side, and we cut that in half to get this individual arc measure of 129.5. Can't we also do the same thing with the length around the circle? The arc length from A through C to B, that distance around is 112 meters. So let's just cut that in half as well, because this is going to be half the size of that total. So that'll save us a little bit of effort. We don't have to set up the proportion all over again. So that'll give us a result of about 56.28 meters. Part E, we're looking at another measure of an arc. This is ABC. So A, B, C. We already have these numbers. You can see we have the arc measures, the degrees around the side. So let's add those up. The 101 and the 129. So that's 230.5 degrees. All right, so again, notice we did not need a proportion here because we had the information already on the diagram. Here's the last one. Let's find the length of arc BAC. Now I'm seeing length and I'm thinking I probably need a proportion, but let's double check. The length of arc BAC. So we're going to go from here to here to here. All right? And yeah, we do need a proportion because we don't have these lengths ready to add up. We do have this length, the 56.28, that represents this distance around the circle from B to C, which is also this distance around from A to C. But I don't have a length here to just add with the 56, so I don't have this number yet. So let's use this as one continuous arc to set up a proportion and find that total length around the circle, using those many degrees as its arc measure. All right, so here is my arc length over the circumference, which we already figured out over here in part C. So 156.45 meters. And that'll be out of 360 degrees. So again, we want this arc in its measurement. So arc BAC is going to be a total of 101 degrees plus 129.5 degrees. So that's 230.5 degrees. So again, those degrees will cancel out. Again, we'll multiply both sides by the 156, and we will get an answer of 100.17, and that's in meters. So those are the basics of what we're taking a look at today. We're going to expand on this slightly by just kind of thinking a little bit about movement around the circle. Because if we're talking about distance around the circle, then we can also talk about how fast are you moving around the circle. And that brings up objects that move in a circular pattern. And for instance, we can take a look at a CD player or a record player. There's an old picture of one, and you would put the needle on the record, and as the record turns, the needle would, get the bumps off of that record and transmit the sound through the speakers. So let's think about your position on a circle as it's turning. We could also use an example of a merry-go-round. That's a good example because you could be riding on the edge of the merry-go-round, or you could be riding closer to the center of the merry-go-round. Kind of like this record player. The needle could be closer to the center, or it could be closer to the edge. So let's just kind of think about this for a moment in these last two questions, all right? So let's talk about just one revolution. We're going to go one time around the circle. So let's talk about distance first. How much farther? So this is not speed yet, but this is just farther. How much farther does a point travel if you are 10 centimeters from the center of the record as opposed to if you are close to the center, if you're just 3 centimeters away? So it's the same record, but your position is different. So here's the record, there's the center of it, and let's say you're at the furthest distance, so let's say you're on the edge, let's say that's the 10 centimeter mark. So the question is, how far do you travel? So if you were to go around that circle, that would be your circumference formula. So circumference is, this is a radius, right? So 2 pi r. So 2 times pi times the radius of 10. That means you've traveled a total of 62.83 centimeters around that record. Now if you are right here, closer to the center, then your radius is just 3, and you're traveling a much smaller circle, which means you have a smaller distance that you're traveling. So in that case, with a radius of 3, you are traveling only 18.85, much, much less. So the question is, how much farther have you traveled? So let's do a subtraction problem. If you are a point on that circle, how much farther do you travel? We'll take that 62.83 and we'll subtract the 18.85, and we get a result of this many centimeters, 43.98 centimeters farther. So even though it's the same record, your position on the record will trace a different sized circle. So if you're farther from the center, you have a bigger radius, you travel a bigger distance around, so you have a bigger circumference. And if you're closer to the center, you trace a smaller circle around, so that means you have a much smaller distance. However, if you're turning that record, and you're playing that record, the record turns the same speed, right? The record doesn't like speed up, or the record doesn't slow down. The record is turning the same speed every single time. So now we want to think about your placement on the record and how fast it appears you're traveling, because the speed is the same whether you are away from the center or closer to the center. The record is turning the same, but a point on that circle will feel faster. It'll feel like you're moving faster if you're farther from the center. To make that a little bit clearer, let's talk about riding the merry-go-round. All right, here they're using the word carousel, but that's your merry-go-round, right? So here we have two people. Kendra and her mother are riding the carousel, and you've got these two horses on that carousel, the merry-go-round, that are side by side. So the question is, where should you sit to feel like you're moving faster? For a more exciting ride, should Kendra sit on the inside horse or the outside horse? All right, so here's your merry-go-round. You've got these two horses side by side. We're turning this way. There's the center of the circle. If you are in the inside horse, this is going to be the path that you take. And if you're on the outside horse, this is going to be the path that you take. And it's a much bigger path. But the merry-go-round is going to be traveling at the same speed. Once it accelerates at the beginning of the ride, once you're in the middle of the ride, the merry-go-round isn't slowing down or speeding up. It's going the same speed over and over and over again. But you may have experienced that if you ride the merry-go-round, your position here, further from the center, makes you feel faster. And if you are here closer to the center, it feels more tame. It doesn't feel as faster, right? And that's because you are covering more distance in the same amount of time. And with a smaller circle, you're covering less distance in the same amount of time. So if you're covering more distance, that means you have to go faster to cover more distance in the same amount of time. So to answer the question, you want the outside horse to feel a faster ride, or a more exciting ride if that's your thing. Why is that? Here's our little explanation. Because we're traveling a farther distance in the same amount of time. And remember, how do you calculate your speed? Well, your speed is found by taking your distance and dividing it by time.